Good morning, everybody. Welcome to today's expert webinar, Effective Genset Controls in a Microgrid with Bachelor expert Denny Raymond. A couple of items before we begin. Today's presentation is being recorded and will be available for on-demand viewing using your registration log or on our Bachelor Electric YouTube channel. Handouts are available for participants in the handout section of this presentation. We have a moderator monitoring the live chat. Any chat messages will be answered in real time. Please enter any questions into the question section at the right side of your screen. Denny will answer questions at the conclusion of his presentation. Any questions requiring follow-up will be answered by email. Be sure to follow Bachelor Electric on Facebook and LinkedIn and stay current with all of our developments happening at our organization. Finally, future webinars will be posted on the Bachelor.com events page. All webinars are free to attend, but registrations are limited to 200 participants. Denny Raymond has 17 years of experience with reciprocating internal combustion engine driven power generation with various makes of engines and alternators. Denny held various roles in maintenance, commissioning, project management, and application engineering. He earned his BS degree in mechanical and engineering and an MS degree from Purdue University in engineering, industrial concentration. Denny is also an EGSA certified journeyman technician and is a Lean Six Sigma black belt. For the past 3 years, Denny has enjoyed guiding technical professionals in effective use of Bachelor Electric's Genset controllers and voltage regulators. And with that, I'll go ahead and turn it over to Denny.
Thank you, John, for the introduction, and good morning, everyone, and thank you for joining. Today, I will be presenting on the topic, effective genset control in a microgrid. The two major goals that I would like to accomplish in this presentation is to define what is required of a genset controller in a microgrid, and secondly, to explore DGC 2020 HD features for achieving these requirements. As most of you know, the DGC 2020 HD is Bachelor Electric's most advanced genset controller that is capable of performing lots of various power management functions, and we will explore why it is a great fit for controlling gensets in a microgrid. But first, let us define what a microgrid is. According to the US Department of Energy, a microgrid is a group of interconnected loads and distributed energy resources within clearly defined electrical boundaries that act as a single controllable entity with respect to the grid. So in summary, you have these distributed resources. For example, solar, wind, gensets are included in that sometimes, and battery storage as well. Oftentimes that's included too. As you can see here in the graphic on the left, you have the utility grid, and then there's some point of common coupling, and then you have the microgrid. Here we're showing a CHP plant, some renewables, a battery energy storage system, and we'll abbreviate that by calling it a BESS system, BESS. And you have electric vehicles. So electric vehicles can be vehicle to grid or grid to vehicle, meaning charging or discharging back to the grid. And the use of electric vehicles to discharge back to the grid in times of need is something that is coming online, and a lot of the utilities are talking about it. You have your reciprocating generators, and then your loads, such as residential, commercial, and industrial buildings. So all of these are together in this little network here, and the loads are very close to the generation sources, as compared to traditional generation, where you had a power plant all the way over here, and hundreds and thousands of miles down the road, you have the loads, and everything was just a radial system where you had the centralized power plant and distribution feeders feeding these loads. A microgrid is a bit different because the resources are distributed, energy resources that is, and the loads are typically very close to these energy resources, sometimes on the very same compound, like a university compound or a subdivision, for example. And one key feature of microgrids is they're able to connect and disconnect from the grid when called upon to do so. So now that we've defined what a microgrid is, let us talk about some unique characteristics of a microgrid. Distributed energy resources, including renewables, And with renewables, you often find battery energy storage systems, BESS systems. And that is because the renewables are intermittent, so there needs to be some kind of storage for when the renewables are not available. In addition to BESS systems, you often find RICE generators, reciprocating internal combustion engine generators. And one of the reasons why they're included oftentimes is for system stability as well as reliability. Renewables and BESS systems are inverter-based generation. The reason for that is because they generate a DC output, and that DC has to be converted to AC because our power system is an AC power system. So that DC has to be converted, and as a result of that, an inverter is needed to do that. So that's why they're called inverter-based generation, IBRs. Renewables are intermittent, and batteries can help, but they typically last only about 2 to 4 hours. So if an outage lasts beyond that, where your renewables are not available, then some other source of energy is needed, and that's oftentimes the genset. Dynamically changing loads in close proximity to the DERs. So for example, here in this system, if this is like a subdivision with all these various resources and loads, and you have multiple EV charging stations, when several EVs are being charged simultaneously, then that adds a huge demand in the local loads. And as a result, the distributed energy resources feel the impact of that. So these dynamically changing loads are something that the power system is not accustomed to seeing, and that has to be controlled and protected in a very unique way for that reason. When gensets are included in a microgrid, then it's oftentimes called a hybrid system. Sometimes you have a microgrid with strictly renewables and BESS systems. At other times, a genset is included, and that's a hybrid system. So that gives you more dispatch options. For instance, you can optimize the microgrid to dispatch to meet some objective, some higher order objective. For example, economics. If an aggregator or a developer wants to dispatch the microgrid to achieve the best economics, then he's going to give priority to those resources that are least costly. Another objective could be environmental emissions. Another one could be power system stability. So depending on the objective function of the microgrid, then the dispatch priority can change. And oftentimes smart controls are needed to do that because those dispatch priorities can be changed on the fly during operation. And in order to facilitate that, we need advanced communications. For example, Modbus and different types of Modbus or different Modbus protocols, and advanced protocols like IEC 61850 and DNP3. So these advanced communications, advanced controls, a microgrid controller sometimes is a purpose-built microgrid controller. At other times, it may be just a master PLC controlling the entire system. And the way that a microgrid is protected is a bit different from the way that traditional protection is done, because, for instance, a synchronous machine can typically provide 8 to 10 times its rated current to support a fault and clear the fault, whereas BESS systems do not provide as much fault current. And as a result, the protection settings need to be lowered if you're now protecting a microgrid that's disconnected from the grid where there aren't any synchronous machines. So different protection settings need to be active at different times, depending on the configuration of the microgrid, whether it's grid connected, not grid connected, depending on which resources are operating. And the other thing is bidirectional power flow, because traditionally you would have a power plant that would output power radially to the loads. But today, with distributed resources at the grid edge, you have power coming from all different directions. And because of this bidirectional power flow, protection algorithms need to be updated to accommodate that. So now that we've talked about what a microgrid is and the various unique characteristics of microgrids from a power system standpoint, then let us talk about the various modes of operation of a microgrid. There is a standard, and it is the IEEE 2030.7 standard that clearly defines the two states of a microgrid and the various transitions between these states. So the first state is steady state grid connected. That is, you have a microgrid, and at the point of common coupling, there's a physical connection that's made, typically through a breaker. And that is a steady state grid connected state. You also have a steady state islanded state, where at the point of common coupling, the microgrid is disconnected from the bulk power grid. But then you have several ways of transitioning between these two states. You can have a transition from grid connected to islanded in a planned fashion. So an example of that would be demand response, for instance, where the utility calls up and says, at 10 o'clock this morning, Mr. Customer, I need you to disconnect from the grid and start supplying your own power in order to help the grid, because the grid is going to be stressed at that point in time based on demand. Or it may go further to say, I don't want you to disconnect, but I want you to start up all your generators of various types and export power to the grid. So both of these could be a planned transition from grid connected to steady state. But you can also have unplanned grid connected to steady state transitions. For example, a forced outage. Now, when you have a forced outage, let's say a tree falls on a feeder and now that feeder is not available to supply power, then the local generators on site need to supply that power. If the transition is successful, then we have T2, which is grid connected to steady state, unplanned. And an example of that would be standby generators following NFPA 110, where they started to come online to supply the critical loads within 10 seconds. But what if the generators were not available? For example, the controller was not left in automatic mode and the generator didn't start because it received a remote start and now it's not in auto and didn't start. Then you have a blackout period. So an unsuccessful transition would result in a blackout period, and then you would come from a black start state to a steady state island state. And of course, there is the final transition. We skipped over T3 and went to T4, but T3 is steady state islanded to grid connected. So when conditions on the grid have been restored and the power is restored, the feeder is now stable, meaning that the voltage and the frequency are within acceptable limits. We transition back to the grid because it's the normal source of power. So these are the defined states and transitions as per IEEE 2037 in terms of the various modes in which a microgrid operates. Another important concept to understand when it comes to microgrids is grid forming versus grid following. So let us define what a grid forming distributed energy resource is and what a grid following distributed energy resource is. Grid forming means that that resource controls the voltage and the frequency of the microgrid, meaning VF mode. An example of that is island load share. If I have 3 generators parallel together and they all in island load share, then each of these generators will be responsible for contributing towards the voltage and frequency stability of that small system, that local system. A grid forming DER can be a synchronous generator, or it can be an IBR that mimics a synchronous generator. So now with new inverter technology, developers are finding ways to have these inverters mimic the behavior of synchronous machines. And you have now BESS systems, for example, that can behave to some extent like a synchronous machine and be grid forming. These operate as the swing generators because if you have multiple generators in load share, island load share that is, whatever the load is, they ramp up and down as the load changes. So they're swing machines. A grid following DER works a bit differently. It does not contribute to the voltage and frequency of the microgrid. The grid forming DERs do that. The grid following DERs synchronize to the grid, the bulk grid or the microgrid, depending on whether the microgrid is connected or disconnected from the grid. But regardless what bus these DERs are synchronizing to, they just synchronize and they match the voltage and frequency and they follow. Their output is regulated to a fixed active power and reactive power, or it may be a fixed power factor. But at the end of the day, this is PQ mode, not VF mode, so it's a bit different. They follow the frequency and voltage of whatever bus they synchronize to, and they output a fixed power and VAR or power factor level. And this kW and kVAR power factor set point may vary based on different inputs, whether it's over Modbus, an analog signal, contact inputs, logical inputs, etc. But they're regulated to a fixed active power and reactive power or power factor set point. And again, these can be synchronous generators or IBRs. And since the conversation is focused around synchronous generators, I just wanted to highlight that a synchronous machine, synchronous generator, Genset, can be grid forming or grid following. So what does that mean for the DGC 2020 HD? It is important to have a very advanced, flexible controller that can control gensets in all these various modes: grid forming, grid following, and to adapt various protection settings as the system changes configuration, etc. So there are lots of features that are available in the 2020 HD that can be implemented in these complex control schemes. So what we want to do is to equip you with the tools and equipment that will help you work smarter, not necessarily harder. With good equipment, you can achieve a more professional and a better job, and you can do that a lot easier, like this guy right here. So having said that, let's talk about a specific microgrid application. This is just an example with two generators in parallel. So the first part of this, most people are familiar with. You have a generator here, generator 1, generator 2, and this is the breaker for generator 1, the breaker for generator 2. So here's DGC 2020 HD number 1, DGC 2020 HD number 2, sensing the load bus and the generators. And these two 2020 HDs perform synchronization, load sharing, and so on. So from here, going back in the system, most of us are familiar with this. This is just standard everyday island load share. And in our case, it's going to be over Ethernet, which is an advanced form of communications for doing load sharing. And here we have a load bank. So for instance, if you just wanted to load test these generators periodically once a month, maybe for NFPA 110 purposes, then the load bank here gives you the flexibility to do that. But then the system is a bit more complex than just two generators and island load share. Here we have a tiebreaker. And downstream from that tiebreaker, we have a BESS system. So this is our battery energy storage system. It's generating DC. We convert that to AC. And here, this breaker can close the battery system onto the bus. And then there's a PV array that, same thing, they're generating DC and being inverted to AC. And that comes onto the bus as well. We have some loads here. So the loads can be supplied either by the generators or the BESS system or the PV system or all of the above when the system is disconnected from the grid. And then we have the grid on this side. So we may have the normal source of power as the utility supplying the loads this way. And then we can reconfigure the system in several different ways. We can connect to the grid, export power. If the grid is not available, then the local resources here can supply power to the loads. And there are many, many things we can do. So of course, at the point of common coupling, you want to have a utility grade protection relay. And it's going to be doing the connecting and disconnecting, following grid code requirements such as IEEE 1547, etc. And also with the ability to communicate with advanced protocols like IEC 61850 and the NP3, and do other things over Modbus TCP IP, for example. ATS control is also possible. This is the BE1 Flex, our most up-to-date protection relay, which has tons of capabilities. And all of what I'm showing here and more can be achieved with this protection relay. And here also at the mains breaker, you can have an additional 2020 HD that is performing the mains power control function. And when a site of generators, these two, for example, is parallel to the grid, you can parallel these generators to the grid in all these different modes, just a fixed base load value, or you can have import or export mode where at times the generators export additional power to the grid. So the generators provide power to the loads, and then what's left over is sent over to the grid. Or if the generators can't provide enough power, for example, if one generator is not available and you only have one left, and that one generator is not sufficient to supply all the load, then you can import some power from the grid to supplement that. Another possible mode of operation is peak shave. Also zero power transfer, doing soft load transfers, going back to the grid, etc. And all these controllers are connected to this Ethernet switch to form one common network. So having described this system, let's take a look at a few scenarios as it pertains to the various transitions from a grid connected to not grid connected state. Just to define the topology here, so the three 2020 HDs, you have the mains 2020 HD and then generator 1, generator 2. When networked together, they form this segmented bus setup. So we have system A, which is the generators right here, everything on the left side of the group breaker. System B, which is the load bus, which is from the right side of the group breaker to the left side of the mains breaker. And then system C, which is the utility. So that's how the system is being modeled by the network of 2020 HDs. So for the transition to an islanded state unplanned, the sequence of operations is as follows. We want the best system to form the microgrid. That means it starts first and sets the voltage and the frequency. Just an example. And then when the state of charge of the batteries is low, we want the gensets to follow, meaning parallel to the batteries in grid following mode. If the batteries are not available, we want the gens, of course, to come online and form the grid, meaning set the voltage and frequency. So right there, just from that alone, that tells us that the 2020 HDs have to be able to control the gensets in both grid forming as well as grid following mode, depending on various conditions. Transitioning to an islanded state in a planned fashion, we want the gens to come online via soft load transfer. And if we're transitioning to a grid connected state, we want to do a closed transition. At times, we may want to do a soft load transfer as well. And then in a grid connected steady state, we want to be able to control the gens in all these different modes. Zero power transfer you can think of as storm mode, where the system is parallel to the grid, but it's not importing or exporting. It's just ready to take over in the event that there's a utility failure. So here's some settings and logic that I'm showing would have to be implemented in the various types of controllers to achieve each of these different modes. In your gen controllers, then your system breaker configuration would be generated to segmented system. And here's some basic logic that can help achieve that. So this is the default logic scheme in a 2020 HD, where you just have some enunciations and breaker control. In the mains controller, which is doing more of the work in a sense, then you'd want to enable mains field transfer. And all these settings here are going to achieve your automatic transfer function. So transferring to generator power upon sensing a dead mains, and then transferring back to the utility, the 2020 HD that's connected to the mains, and sensing the mains and controlling the mains breaker is going to perform that function. The settings here are all your timers. So the delay time and your return delay time to give the utility sufficient time to become stable. All these settings are listed right here. And all these functions are canned in the firmware. So just by implementing a few settings, you can achieve an entire transfer scheme using a 2020 HD. And then there needs to be some logic for the two breakers. So we showed that the 2020 HD at the mains is also controlling the group 2020 HD downstream. If we're transitioning to islanded mode in a planned fashion, then we can use the load takeover logic element. So what we're saying is we're going to send a load takeover request. And then when the state of charge in the batteries is less than 30%, we want load takeover. Load takeover will start the gens. And if it's in close transition, we will parallel the gens to the mains, do a soft load transfer, and then let the generators take over. If we're transitioning to grid connected mode, then we can do that in two ways. If we're coming out of a planned transition, we need to take away load takeover logic. Or if it's coming from an unplanned transition, then our settings here will take care of that. In the case where it's coming out of a planned transition, like demand response, where it's time to transition back to utility power, we had the load takeover request, but then we set a latch when the state of charge was less than 30%. The state of charge is now at 100%, so we're trying to reset this latch right here. And the latch will finish resetting when the mains is stable after 30 minutes based on this timer. So when this timer times out, the output will be true. Both inputs to the AND gate will be true. The reset input here will be true. And this output is going to go false. Load takeover is going to go away. For the grid connected steady state, like I said, we have several different modes in which we can operate. So we have base load mode, peak shave, import, export. And these can be set in the settings, but they can also be changed on the fly using programmable logic like this. And then based on which mode the system is in, we can also use programmable logic to raise and lower the set point or set various prepositions. We can do more, like receiving direct Modbus writes, using an analog signal, etc. So there are so many different ways to control generators in all these different modes using the 2020 HD. In this system, the gens can be parallel to the grid or they can be parallel to the batteries. But how do we know what they're parallel to? We can implement distributed broadcast logic to determine that. So here, the mains controller is sending out the status of the group breaker, which is this breaker. So you can see this blue line right here. It's receiving breaker status and controlling that breaker. receiving breaker status from the mains and controlling it. In the case of the 52B, the best system breaker, we're not controlling it, but we're only receiving the status of it. So the mains controller right here is receiving the status of breaker 1, 2, and 3, the group mains and best system breaker. And it's broadcasting these statuses over Ethernet to the gen controllers. Now we can take these statuses and determine whether or not we want to set the parallel to mains logic element. In this case, for instance, we're saying that generator breaker 1 is closed, mains breaker is closed, and group breaker is closed. So we have a continuous path to the grid right here, and we're setting parallel to mains. So therefore, we can parallel generator 1 to the grid in any of the 4 desired modes. Whether it's parallel to the battery, we can determine that as well, because here in this case, we're saying that the best system battery is closed right here, and the gen breaker is closed, and we have this Modbus switch that receives a write to go from a false to a true state to say we want the genset to follow the best system. And as a result, we set parallel to mains. If we want the gens to be grid forming instead, then we put a NOT gate behind this Modbus switch. Parallel to mains is not going to be set. And now we're paralleling the gens to the batteries in droop override, droop mode pretty much. And the reason why this can be done, or this would be done, is because typically in a grid forming setup where you have multiple resources that are grid forming, like generators and batteries, then droop is the de facto standard for achieving that, at least with today's technology. So what have we learned? That microgrids with gensets are becoming more popular. Genset control is more complex when you have a microgrid than just a typical standby setup. Genset should be effectively controlled for the various microgrid states, which are either islanded, which is disconnected, or grid connected. And for the various transitions, such as grid connected to islanded, unplanned, grid connected to islanded, planned, islanded back to grid connected, or black start. If your transition to an islanded state failed, you go through a blackout period and then transition from black start to islanded. The flexibility of the 2020 HD makes it a great fit for all these various microgrid applications. So with that, we'll take some questions. Just remember that you can contact us 24 hours a day, 7 days a week, 365 days a year at this number and email address. If you don't as yet, please request an account on Basler.com to gain access to all these resources. If I don't have time to get to your question, please email me, DennyRaymond@Basler.com, and I will respond as soon as possible. Let's open up for questions.
Great. Thank you, Denny. Okay, we had one come in through chat. The question is, how do we balance the import-export of power to the utility with facility load and cost kilowatt hour rate while avoiding unnecessary islanding?
Interesting question. So there are settings in the 2020 HD mains power controller that allow various export and import levels to be set. These can be fixed levels, or they can be adjusted using the raise and lower inputs that I showed using the import-export logic element. We can set various fixed preposition levels, or if these are dynamically changing, they can be adjusted by an analog input or Modbus writes from a master controller, like a microgrid controller or a PLC, for instance. So some other controller or some, I guess, some source of information has to tell the mains 2020 HD what import and export set points are desired. And once the 2020 HD gets that information, it sends speed and voltage raise and lower signals to the gen controllers to ramp up or down to achieve that level of import and export.
Great. A couple more questions. Does the genset need to be shut down and restarted to transition from grid following mode to grid forming mode?
No, it does not. All it takes is just changing the status of the parallel to mains logic element, and that takes place within milliseconds. From a control standpoint, it does not. The controller will process that logic very fast within milliseconds and make those adjustments. It's more a question of whether the genset can handle the bump in the transition. So if, for instance, the machine trips on overload or some other protection setting, then it trips offline and it may shut down depending on how that protection is set and the capabilities of the machine to ramp up and down. Because obviously, if the machine's grid following then it would have to regulate its output differently when it switches to grid forming. So it's more it's more a question of the machine itself as opposed to the controls. From a control standpoint, no, it doesn't need to be shut down.
Okay, a question came in about the DGC 2020 HDs. Any forecasted improvements in the future? How about the VRM 2020?
Not sure what specific improvements are being referred to, but as Basler Electric, we continue to always look for opportunities to grow. We try to keep up with trends in the market, and we believe in continuous improvement. And we every a few times a year we keep on making firmware upgrades, and those firmware updates include enhancement features, etc. So the product keeps on getting improved. If you look at what it was 6 years ago compared to now, there's a lot of growth that has taken place as far as feature enhancements and additions.
Okay. There's a couple questions about lead times. We don't have any information on that currently. We'll get that answer to you in email if we can dig up some info later. Another question came in. How is an inverter-based resource different from a synchronous machine?
A synchronous machine has inertia, an inverter-based resource does not. So that's one of the big differences. And as a result of that, they behave differently. So a synchronous machine is already spinning. It's easier to have it ride through a fault. And they tend to be able to contribute high levels of fault current, sometimes up to 8 to 10 times their rated current, to ride through a fault and clear the fault. An inverter-based resource does not have inertia inherently. So any of the behaviors that it tries to mimic of a synchronous generator has to be achieved either for software or for some other type of control circuit. But it's basically artificially trying to mimic those desired intrinsic behaviors of a synchronous machine.
Great. Okay, another question. How much time it will take to dispatch the power from inverter-based resources under black start condition?
It depends. So I understand that BESS systems started pretty quickly. And that's one advantage of not having inertia, because if you're already spinning, then inertia works for you. If you're coming from a dead state and you're trying to get up and running, inertia works against you. So in that case, a BESS system having no inertia, it gets up pretty quickly. So I can't give, I guess, numbers as statistical data, but that's my general understanding of how that works.
Great. Do you recommend specifying redundant Basler relays?
So I guess I want to understand the specifics of what relays are being referred to. If we're talking about utility grid protection relays or like controllers, for example, the 2020 HD that has some relay capability. It all depends on the application and the specifications, the requirements, etc. for the project. But I don't know that there's a blanket answer I would give. What I will say is that our products are very reliable. So we have not found the need on the control side, I could speak for, to have redundant controllers because the controllers are so reliable. But if a spec calls for it, or it's a requirement maybe within a certain jurisdiction, then certainly there are ways to achieve that.
Great. I don't know if you can answer this question about synchronous machines. We actually had a presentation a couple weeks ago on synchronous machines. The question is, to what extent could a synchronous condenser emulate the desired behaviors of a synchronous machine versus solid state systems?
So I think that that would be a question I would want to get back to.
Okay.
So yes.
Great. Well, that looks like all of the questions that came in online. Again, if anybody had any additional questions, go ahead and enter those. We'll collect those up a little bit later today, and Denny can get back to you via email. So once again, thanks again, Denny, for your presentation. Appreciate the valuable information. We have one more of our expert webinars, a relay review on the May 29th with Daisy Mora, and then we're taking a break for the summer. We'll start back up again in the fall. We have 8 more presentations we'll be doing at the end of the year. As always, if you go to Basler.com, look at our events page, the registration information is there, and the other trade shows and places where we'll have Basler employees. Other than that, we wish you a good day. Thank you again, Denny.
Thank you.
Take care, everybody.